Here's something that should bother you. The compound I'm about to describe has been protecting industrial cooling systems from the inside out for over 70 years. It costs $2, and the automotive coolant service industry generates over $4 billion a year in recurring flush and fill appointments, while most drivers have never once heard its name. That's not a coincidence. The answer starts in the early 1950s, in the cooling towers of heavy industrial facilities, the enormous open-air structures, rising out of steel mills and chemical refineries, exhaling steam into the winter air. The engineers running those plants had a serious problem. Water circulating continuously through miles of metal piping, day in and day out, at high operating temperatures, with dissolved oxygen and mineral salts working on the interior surfaces around the clock. They weren't fighting rust you could see and scrape off. They were fighting electrochemical erosion, the slow, invisible migration of metal ions off the pipe walls, leaving behind a weakened, pitted surface that eventually failed without warning and without any visible signal beforehand. They tried the obvious solutions: pH adjustment, phosphate treatments, biocides, scale inhibitors. None of them addressed the root mechanism. And then, sometime around 1953, a process engineer at a chemical plant in Baton Rouge tried something the academic literature had hinted at for decades, but nobody in heavy industry had implemented at full scale. He added a silicate compound to the circulating water. Not as a cleaner, not as a descaler. As a passive film former. Within one cooling cycle, the bare metal surfaces inside the system, the pipe walls, the pump housings, the heat exchanger faces were coated in a transparent, microscopically thin, continuous layer of silicon dioxide. The same fundamental chemistry that makes glass. Bonded directly to the metal. Sitting between the water and the wall. The corrosion problem didn't slow down, it stopped. By the early 1960s, the silicate film forming approach had been adopted across American heavy industry nuclear power plant cooling loops, large-scale HVAC systems in commercial buildings, diesel locomotive cooling circuits operated by major freight rail companies. Any system where water touched metal continuously, and where failure was expensive enough to take seriously, was running on this chemistry. And here's where the history gets interesting. That same principle had been quietly running in marine engineering for 2 decades before any of that. Ship engines circulate water through their cooling passages, often salt water, which is roughly 30 times more corrosive than anything in a car's radiator. Loaded with chloride ions that attack iron and aluminum at the electrochemical level with a methodical patience that outlasts any temporary coating or sealant. British naval engineers in the 1930s had already documented that silicate-based compounds added to cooling circuits formed a self-sealing passivation layer 1 that bonded to the metal, survived repeated high-temperature cycling, and self-repaired wherever it was disturbed by vibration or pressure change. The vessels running this treatment outlasted comparable ships by measurable margins, with cooling components remaining within specification far past the expected service life. It was in the Admiralty's own engineering records. It was known. Soviet industrial engineers independently arrived at the same chemistry by the late 1940s, applying it to locomotive cooling systems along the Trans-Siberian Railway completely separately, on the other side of a Cold War, using the same compound. Independent convergence. Different nations, different languages, different engineering cultures, all landing on the same solution. That kind of convergence doesn't happen by accident. And for most of the 20th century, all of it sat in naval specifications and industrial chemistry journals, present, documented, functional, and completely invisible to anyone buying a car at a dealership. You already know this reaction. You've seen it your whole life and just never connected the dots. Think about what happens to a cast iron pan that's been properly seasoned over years, that dense, jet black, almost glassy finish that builds up on the cooking surface through repeated use. The iron underneath isn't in contact with air or moisture anymore. The layer between the metal and the environment is doing all the work. It doesn't peel. It doesn't flake off under normal use. And when it gets scratched or disturbed, it rebuilds itself at the edges because the chemistry that formed it is still present and still active in the oil and heat around it. Silicate corrosion inhibitors work on an almost identical principle inside your cooling system. When the compound is dissolved in the coolant, it travels through the entire circuit on thermal convection currents, reaching aluminum cylinder heads, cast iron engine blocks, steel water pump housings, brass fittings, copper radiator cores. At each metal surface, it bonds at the molecular level, depositing that same continuous, glassy, self-repairing film. A few nanometers thick. Invisible under any normal inspection, but completely unbroken across every metal surface the coolant touches. A mechanic who opens a cooling system that's been running with silicate inhibitor for 100,000 miles will find a surface that looks almost like new casting clean, uniformly colored, without the pitting and the reddish-brown streaking you'd expect at that mileage. It looks different because the electrochemical process that normally changes the surface over time simply hasn't been running. And because the compound stays active in solution, that film self-repairs wherever it's disrupted by normal vibration, by pressure pulses from the water pump, by the thermal cycling between a cold morning start and a fully warmed engine at highway speed. The layer isn't passive once it forms, it's continuously maintained by the chemistry still suspended in the coolant around it. And because the barrier is purely electrochemical separating the reactive species in the water from the metal they need to reach, there is no pathway for the corrosion process to restart. The physics doesn't negotiate. The mechanism removes the conditions corrosion requires. The timeline for this matters. In a clean system, fresh coolant, recently flushed, the passivation layer forms within the first 2 to 3 hours of engine operation. Not after a week of driving, not after 500 miles. Within 1 or 2 normal drives. In an older system with some light surface oxidation or loose deposits already present, the compound does 2 things simultaneously. It suspends and carries away the loose material while laying down the passivation layer on the clean surface underneath. You'll sometimes see a faint brownish tinge develop in the coolant reservoir over the first week. That's the suspended material being carried out of the circuit and collected, and then the coolant gradually clears as the system stabilizes. Not instant, but as close to permanent as cooling system chemistry allows. A treated system stays protected as long as the compound remains in solution and you're refreshing that concentration every time coolant is topped off or changed. Now, here's the question nobody in the industry wants you to ask. If this compound exists, if it's been in continuous industrial use since the 1950s, if it's written into the maintenance specifications of British naval vessels, American freight locomotives, and nuclear power plant cooling loops, why does a standard coolant flush and fill service cost between $150 and $200, recommended every 30,000 miles at shops across the country? You already know the answer. A $2 compound that permanently maintains the protective chemistry of a cooling system that a customer is currently paying $300 to $400 every 2 years to have periodically flushed and refilled is not a business model. It's a business ending. The automotive coolant service industry generates over $4 billion annually in North America alone. That revenue depends entirely on the predictable degradation of your cooling system's protective chemistry on the assumption that it breaks down on a schedule, and that the solution is periodic replacement, not prevention. A compound that maintains that protective chemistry continuously, from the first drive to the 300,000-mile mark, doesn't fit that model. It fits inside your engine, but it doesn't fit the revenue structure built around it. Bad and bad. Here's exactly how to use it. And the mistakes that make it fail. First, the critical selection note. What you're looking for is a silicate-based cooling system corrosion inhibitor, not a stop leak product. Not a coolant booster or a flush concentrate. Not a radiator sealant. The compound is sodium silicate, sometimes sold as water glass in its industrial form, or a concentrated silicate corrosion inhibitor available through commercial fleet supply companies and most larger auto parts stores. It comes in liquid concentrate or in tablet form, depending on the brand. What you're looking for on the label: silicate corrosion inhibitor, cooling system passivator, or a sodium metasilicate-based formula. The liquid concentrate is a clear to pale amber fluid, slightly viscous, with a faint mineral smell. The tablets dissolve completely in the coolant within 1 heat cycle. You won't find residue or sediment if you're using the right product. Price point: under $2 per treatment dose for a standard passenger vehicle. That's the entire parts list. Application is almost embarrassingly straightforward. Engine cold. Locate the coolant overflow reservoir, the translucent plastic tank connected to the radiator by a small hose, not the radiator cap itself. Add the treatment dose calibrated to your system's total coolant volume. Most passenger cars hold 8 to 12 liters total. The treatment dose is typically 1 tablet or 1 measured cap of concentrate for that range. Replace the cap, start the engine, let it reach full operating temperature. That first complete heat cycle is what activates the compound and begins the film forming process. Drive it normally from that point. The compound works silently, invisibly, continuously, for as long as it remains in the system. Here's the one thing people get wrong when they first try this. They add it to a cooling system that's been neglected for years: dark rust-colored coolant, visible sediment in the reservoir bottom, a system that's never been flushed, and they expect the compound to correct the accumulated damage. It won't. This compound prevents corrosion from forming and slows its progress once started. It can't reverse mechanical or chemical damage that's already done. If your system looks like that, flush it first with clean water, refill with fresh coolant, and then add the inhibitor. Clean foundation first, then protection. That sequence is the whole method. The real-world case I keep coming back to is a 2006 Honda Accord 2.4-liter four-cylinder, manual transmission documented running past 340,000 miles on its original water pump and original radiator. The owner had added a silicate corrosion inhibitor to every coolant change since the car left the dealership. 340,000 miles. Original water pump bearing. No head gasket work. No radiator replacement. The components that cooling system corrosion attacks, first the aluminum head surfaces at the coolant jacket, the pump impeller and housing, the thin-walled tubes of the radiator core were all still performing within factory specification at inspection. That's not an accident, that's the chemistry working the way it was designed to work in a Baton Rouge chemical plant in 1953, applied to a different engine in a different century. One honest limitation that belongs here. This compound prevents electrochemical corrosion. It does not fix existing leaks, seal cracks, or restore a water pump bearing that's already worn through. If your cooling system has a current mechanical problem, a weeping hose connection, a slow radiator seep, a thermostat that's sticking intermittently, the inhibitor won't resolve that. What it does is halt the microscopic degradation process that gradually converts a fully functional component into a failing one over tens of thousands of miles. Preservation, not repair. Two different tools for two different problems. That distinction is worth holding on to before you start. Here's the part that stays with me. In 1953, a process engineer in Louisiana solved a corrosion problem that had been destroying industrial infrastructure for decades with a $2 compound and a working knowledge of electrochemical film formation. That solution spread into naval engineering specifications, into the maintenance manuals of industrial cooling towers, into the written protocols of the kind of fleet operators who measure their success in seven-figure odometer readings. It was never hidden, it was never classified or restricted. It sat in published engineering journals and industrial trade publications for anyone who knew where to look. And somewhere in the distance between the industrial plant and the consumer garage, a completely different model took hold. Not built around preservation. Around replacement. Around the flush interval. Around the idea that your cooling system is a consumable something designed to degrade on a predictable schedule, to be serviced and degraded again, in a cycle that repeats conveniently every 30,000 miles and generates $4 billion a year for an industry that has never had a financial reason to interrupt it. I'm not angry about that, genuinely, I find it more sad than anything else. Because the people paying for those flushes every 2 years aren't careless or naive. They're doing exactly what they were told to do by people who had clear financial reasons to keep telling them to do it. The engineering that could have interrupted that cycle was sitting in a chemistry journal the entire time. It just never appeared on a service center's wall. There's something almost philosophical about that, about how knowledge and commerce travel through different channels, at different speeds, and how the gap between them is where most people end up paying. Knowledge like this doesn't disappear on its own, it gets buried. This channel digs it back up. Subscribe if that matters to you. I don't know what brought you here. Maybe your coolant light came on last week and you started following a thread you didn't expect. Maybe you just got quoted $175 for a flush and something about it didn't sit right. Maybe you're just the kind of person who genuinely cannot put down an old engineering manual once you've picked it up. Doesn't matter, it works either way, now you know how. Take care and I'll see you in the next.